Alright, in this video I'm going to do a problem that is a little bit more complicated than the last force problem, so I'm going to actually involve vectors in this problem. So let's say I have a proton sitting here, and over here I have an electron, and over here I have another electron. And we'll say the distance between this proton and this electron is 0.03 meters. And the distance between this one is 0.02 meters. Now, if I were to draw a free body diagram for this situation, what you do is you put yourself in the position of the charge in question. So if I want to know which direction is the proton going to go, I would put myself in the position of the proton and then draw the forces relative to that proton. So as a result of this electron, the proton is going to want to be pulled to the right. We'll call that force electric 1. And as a result of this electron, it's going to want to be pulled to the left, and I'll make that vector a little bit longer because I know that even though the charges are the same, these two are closer, so this force is going to be stronger. So if I really wanted to draw like my net force, the net force is going to be this one minus this one, so it'll be a little bit to the left in that direction. Now, in order to calculate that, I'd have to figure out the magnitude of this and subtract this. So let's just go ahead and do that. So I'll start by figuring out the second one. So I've got 9 times 10 to the 9th times the charge of a proton times the charge of an electron, all divided by their distance squared. Now notice that I did not make the electron and the proton positive or negative. I just made them both positive. The reason is because I have already figured out, remember that charge and really pluses and minuses really just indicate direction. But I've already drawn my free body diagram. I already know the direction that it's going to go. So I really just want the magnitude so that I can subtract the two and figure out the net force to the left. So whether or not you make the electron positive or negative isn't really going to affect it. It would just indicate direction. Alright, so I do second EE to the 9th times 1.6 to the negative 19th times 1.6 to the negative 19th. And then I'm going to divide that by 0.02 squared. And I get 5.76 times 10 to the negative 25th newtons. Okay, now let's go ahead and do the one to the right. So that's going to be the same up top. 0.6 times 10 to the negative 19th. Sorry, that's parentheses there. 1.6 times 10 to the negative 19th, all over this time 0.03 squared. All right, so 9 to the 9th times 1.6 to the 19th. And then divide that by 0.03 squared. And I get, in this case, 2.56 times 10 to the negative 25th newtons. So I know to the left I'm going this, to the right I'm going this. So I just need to subtract those two values from one another. So 5.76 to the negative 25th, and then subtract from it 2.56 to the negative 25th, which is going to be 3.2 times 10 to the negative 25th newtons. All right? And I know that the net direction would be to the left. All right? So just remember that electrical forces are vectors, and so we would have to either add or subtract and be able to draw a free body diagram so we could figure out a net force. Now, just so we can look at something, we're not going to perform a calculation with this, but let's just kind of look at another couple of scenarios where we're just using vectors and just sort of qualitatively explaining. So let's say I have the proton here, and now I put an electron here and an electron here. The proton, we put ourselves in the position of the proton. We know that as a result of this electron, it's going to want to go down. As a result of this electron, it's going to want to go right. And so my net force would be in this direction. All right. Let's say I replaced one of those electrons with a proton. So let's say I've got a proton here, and now I make this a proton and keep this an electron. Now this force is still the same. However, this one's repelling it, pushing it, so he's going to want to fly that direction relative to this. So the net force would be in this direction. All right. So we could also do vector math and figure out what this is based on their distances and whatever, but let's just not keep it that complicated. Let's go ahead and just look at them qualitatively. So just remember that force is a vector, and so we have to think about the direction as well as the magnitude when we're dealing with multiple charges.